Welcome to CDR Horizons, a new series from OpenAir hosted by Charles and myself, Harsh, in which we engage leading researchers about novel carbon removal technologies they're developing in their labs. CDR Horizons will explore the future of removing carbon dioxide from the atmosphere, and we're excited to have you on this journey.
In this episode, we speak with Professor Rafael Santos, a professor at University of Guelph, about his research with enhanced weathering of wollastonite. Enhanced weathering is a carbon capture technique where mineral compounds found in certain types of rocks can capture carbon dioxide. In this discussion, Professor Santos shares the results of his recent fieldwork in Canada using wollastonite for carbon capture, and we discuss the various advantages wollastonite has over other compounds for enhanced weathering. If you're interested in following more research, definitely like and subscribe to our channel for more content. And now, on to the show.
So today I would like to tell you a little bit about my work with enhanced weathering here in Guelph and what some of my colleagues have been helping us to achieve. And the idea is that enhanced weathering is a way of capturing CO2 in agricultural soils through the addition of minerals. And the mineral that we'll focus on today is called wollastonite. So the very first thing I would like to comment on is that when considering what mineral to add to agricultural soils, the idea is that we have a few options. And one of the key considerations should be the distance between the mine and the point of application. Of course, abundance of the mineral is also important. So we need to find minerals which are available in as many places around the world as possible. Now, having said that, the reason why we use wollastonite is because not only is it available in reasonable quantities, and it's available very close to us. We have one of the few commercial mines of wollastonite here in Ontario, Canada, but also wollastonite is the fastest weathering natural mineral that is abundantly available. And so that allows us to study enhanced weathering in a faster way and therefore be able to see its effects more quickly. The other thing to consider about wollastonite is that when you look at this map here and you look at the table that I've presented below, which come from very frequently cited sources, one of the key considerations is that the market for wollastonite until today has been focused on metallurgical applications and other industrial applications where there are certain properties of wollastonite which are very important. And those could be particle size, particle shape, it could be purity, it could be even whiteness, opacity, and etc., optical properties. For agricultural applications, those properties are not quite as important. The main property that we look for is the ability to weather and the ability to sequester CO2. So that can actually open up the opportunity for mining of wollastonite in places not before considered. So the estimated reserves of wollastonite that we have today might be an underestimate if we also consider some of the less suitable reserves for other applications. Now, the other important thing to consider in enhanced weathering is that not only do we want to sequester CO2, we want to also be able to benefit plant health and soil health, because that's a way of convincing farmers to use minerals in their practices. So we often speak of what are called the co-benefits of enhanced weathering. And so the co-benefits of enhanced weathering can include supporting plant growth. It can include properties such as being antifungal, properties such as improving water retention of soil, and et cetera, and et cetera. These are some of the effects that we have been studying with wollastonite at the same time that we study its ability to sequester CO2. The other important consideration of enhanced weathering is that being a way of sequestering CO2, it may qualify for carbon credits. But the issue with carbon credits is that to be reliable, we need to be able to verify the carbon sequestration. So a question then comes, what is the method to verify carbon sequestration through enhanced weathering? And the answer is that it actually depends quite a bit on the mineral that you're using, but also the soil, the climate, and a few other factors. In terms of wollastonite, what we've come to find is that we do see the accumulation of calcium carbonate in agricultural soils as long as we are within a pH range where the precipitation of carbonates is possible. If the soil were to be too acidic and precipitation of carbonates is not possible, what we need to realize is that the bicarbonates would migrate down into the soil and eventually into the subsoil, eventually into aquifers, and eventually all the way to the ocean. So enhanced weathering doesn't stop at the point of application. Enhanced weathering is actually a chain of events that leads to the capture and transport of CO2 from atmosphere, soil, subsoil, all the way to the final sink, which is the ocean. And that does make verification a little bit more complicated. If we are not able to verify carbon formation in soil, we would rely more on modeling. And so in our research, we do not only experiments and sample characterization, but also modeling to understand where is the carbonate eventually going to end up. Now I'll go through a series of a few examples of experiments and trials that we have done with Wollastonite here at the University of Guelph in Ontario. The first one I call a pot study because that was the first study that we did. We essentially grew plants in pots with soil and Wollastonite and tried to see what was happening. And what we found was that we need to focus on two kinds of carbon in soil. We need to focus on inorganic carbon, which is the carbon that we're forming, but also organic carbon, because our goal is to increase the amount of total carbon in soil. And so in our studies, we found a couple of things. One is that it is possible to increase the amount of inorganic carbon while still maintaining the same or similar amount of organic carbon, therefore having more total carbon. But also we found that the plants that we use in our pot very much affected the rate and the extent of carbon sequestration. So this particular study actually concluded that leguminous plants, such as soybeans, green beans, are able to sequester more CO2 because they enhance the weathering. So it's already called enhanced weathering when you put minerals in soil because you have water, you have acidity, you have microbes. But when you have leguminous plants, it enhances even more the weathering rate. And that's something that we were able to verify in these pot studies. The next kind of study that we have done is what we call microplot study. A microplot study tries to simulate a little bit more closely what happens in the field, but again, under conditions which are controlled. And those control conditions allow us to test things that we wouldn't otherwise be able to test in a field trial. And one of the main parameters that we were interested to study was the amount of mineral. How much mineral can we actually put in the soil to have the carbon sequestration and still have the co-benefits of increased plant health and soil health? So in this graph, you see an example of one of the experiments that we did. We grew 3 different plants, a soybean, green bean, alfalfa, all of them leguminous. And we increased the amount of Wollastonite in soil all the way from 1.5 weight percent in the microplot up to 20%, which is actually a very, very large amount of Wollastonite. And we did find that after a certain point, the plant growth was negatively affected, and the carbon sequestration also became negatively affected because of the now absence of plant activity, right? So the two things are tied together. Good plant activity helps weathering, and weathering helps good plant health. And that was very clear just by looking at the plants. These are pictures of the alfalfa plants, and you can see that if we increase the amount of Wollastonite too much, eventually we see negative effects on plant growth compared to the optimal. So that's something that is important to consider when applying minerals in agriculture. We need to be careful with what limits we can support with good plant health and soil health, but also even the practical aspects. We always have to remember that it is an extra cost for a farmer to choose to apply minerals to their soil. So the application rate is something that will affect their bottom line of their economics of their agricultural activities. And the second thing also to consider is the actual application. Farmers are used to spreading fertilizer, pesticides, and even minerals such as a limestone in their soil. So they have certain equipment which are meant for certain application rates. When we went to our field trials, which I'll exemplify next, we did consider that we needed to use application rates that were matching the typical application rates of limestone so that we could use the same methodology, the same equipment. And again, that is in line with the idea of not overdosing the soil with minerals to support plant health and soil health. So then we can move on to our field studies. We've done a few different field studies here in Ontario. I'll be explaining a few of these fields that you see on this map. These are all in southern Ontario. One of them, field number 1, was in the town of Paris, Ontario, which had a leafy vegetable field, essentially lettuce. The second field was in a town of Alliston, that was a potato field. And the third field was in the town of Woodstock, that was a soybean field. Now, the interesting thing about these 3 fields that we see here is that we were not the first ones to apply wollastonite to these fields. The farmers had already been using wollastonite for several years because they saw benefits to the wollastonite beyond carbon sequestration. In the lettuce farm, for example, the farmers felt that the lettuce grew better. It would stay fresher for longer when transported to a supermarket, for example. In the potato farm, they felt that the potatoes would be larger, stronger, more nutritious because of wollastonite. And in the soybean field, the idea was that it supports yield, but also supports the reduction of the need to use pesticides because of anti-fungal and anti-insect properties of wollastonite. So in all of these fields, what we did is that we did the soil sampling to determine the amount of carbon in the soil. We did track changes in carbon through time. And in all of the fields, so in different soil conditions, slightly different climate conditions, and different crops, we always found that the presence of wollastonite did increase the amount of carbon in the soil, specifically the amount of pathogenic carbonates, which are the carbonates that we detect through a technique called calcimetry. So finally, I'll just wrap up with a little bit of an outlook of what else can we do in terms of enhanced weathering. What are some of the outstanding questions and opportunities? One of the things that we have to consider is that up until today, the inorganic carbon cycle in soil has often been ignored because we tend to think of soil as being the top 15% or top 15 inches of soil where we don't find much naturally occurring carbonates. Right? The naturally occurring carbonates, because of their ability to migrate with water infiltration, they tend to accumulate in the subsoil. And so in the soil sciences, it's often a forgotten subject unless someone is actually specifically trying to study what's happening in the subsoil. So we do encourage future studies on soil carbon sequestration, regardless whether it be through enhanced weathering or not, to always remember that we do have 2 kinds of carbon in soil. We have organic carbon and inorganic carbon, and the goal should be to increase the total amount of carbon, not just one or the other. So these techniques can definitely work simultaneously and to achieve the same goal. The other thing that we propose is that with the exemplification of enhanced weathering in various studies, it's not only our group, there are many groups around the world using enhanced weathering and showing positive results in soils and other land types, that we can now consider this to be a reliable approach, and we can start thinking of the next steps of how do we verify the carbon sequestration, how do we ensure the permanence of the carbon sequestration, and how can we qualify the farmers and the land managers who are using these minerals to qualify for carbon credits, right? So on the right-hand side there, what we show are the climate change mitigation wedges, and we propose that enhanced weathering, both in agricultural settings, but also other settings such as urban farming, should be considered to be reliable ways to sequester carbon. So lastly, I would just like to introduce you to the team who has been doing all this work here in Guelph. The principal investigators have been myself, Rafael Santos, and also Professor E.Y. Chang. And we have had a number of graduate students and postdocs come through our labs to do all the work that we have done to date. In the center is a picture showing some of our field trials and our past students. We had Dr. Fatima Hake, Hugo Fantucci, Stephen Vanderburg, and Maria Aguirre. And then in the bottom, we see our current members of our team working on enhanced weathering. We have Francisco Araújo, Reza Khalidi, Asif Ali, and Hiral Jariwala. And each of them is working on a different aspect of enhanced weathering, some focusing more on experiments, some focusing more on modeling, some focusing more on carbon sequestration, some focusing more on plant and soil benefits. And so we do hope to have exciting results coming up in the next few years through some of this work that we have been doing. So thank you for your attention.
Professor Santos, thank you so much for sharing some background on enhanced weathering and Wollastonite. I think just to start off, for especially some of our new viewers, the question is like, why does enhanced weathering matter, right? So I know it like helps with carbon capture, but what if we don't do this? What are the alternatives, or what's the problem it's solving?
So essentially, enhanced weathering is one of the tools that we have in the toolbox for climate change mitigation. So we definitely don't want to say that it's better than all the other tools. Each tool has a different purpose and a different ability. What attracts me a lot to enhanced weathering is the scale. It's a technology that does have a large scale that can be scaled up to the order of gigatons per year. The other benefit or attractive aspect of enhanced weathering is the safety and the reliability. So it's a technique that has a small chance of the CO2 not being permanently sequestered, and it has also small chance of having negative environmental impact. So if we were to plot a graph of capacity to sequester versus risk and safety, I would say that enhanced weathering would be very close to the top right corner, along with some other technologies. So there are other technologies that are definitely very worthwhile. As I presented in my presentation, enhanced weathering really makes sense if you have the right mineral supply close to the point of application. And we definitely won't have the right mineral supply close to every farm in the world or every land in the world. So there are still many countries and many even continents that where enhanced weathering might not be the best approach. And so other approaches can be considered.
Yeah, that's very interesting. I'm wondering, like, to your point about permanence, at least from a first principles perspective, a lot of this like CO2 came from the ground and now it's in the air and we're depositing it in the ocean. And it seems like, the source and the final destination is different than it, like naturally was earlier. Does that have any impacts on like other systems on the planet, or is that like, is the quantity small enough where it's not really making a big difference to the actual ocean ecosystems?
Well, the idea is that the fossil fuels were also accumulated at the bottom of bodies of water. And so it was organic matter that somehow went to the bottom of lakes and oceans, and eventually a sediment fell on top of it, and it came under pressure, and then it turned into natural gas and petroleum. So when the carbonates end up in the ocean, they also will precipitate and fall to the bottom of the ocean and accumulate there. So it's part of already of the global carbon cycle. So it's not that different than the way nature does it.
That's awesome. Yeah, we're finally completing the cycle. How did you end up studying enhanced weathering for carbon sequestration? What was your kind of journey to this topic?
So I would say that I first learned about enhanced weathering, especially when it comes to adding minerals to soil, from my colleagues in the Netherlands. My colleague Paul Knops once did a study using olivine in soils and trying to grow some plants, and they published a paper in PLOS ONE on that. And I believe that was really my source of inspiration. When I came here to the University of Guelph, it's a university that specializes in agriculture. And so I was trying to figure out what type of research I could do here to try to better integration with existing researchers and funding opportunities, and et cetera. Then that was the inspiration, adding minerals to soil. Then the key thing was that my colleague Paul Knops introduced me to the company here in Canada that was mining wollastonite. And that's when I came to know that they actually were already using wollastonite in agriculture. They were already commercializing it to many farmers. And so that helped us a lot, because not only it sped up our research, but it gave us confidence that it was something that was widely accepted. So it's a much lower barrier to overcome if people are already using it and trusting it.
You mentioned doing work with miners and reaching out to them, and you've shared with us the results of your field experiments out with the different agricultural plants. What was kind of the process of like reaching out and getting involved in these kinds of experiments? And do you have any reflections maybe to share with us on the challenges of doing field work and maybe the challenges of scaling this R&D out in the real world?
So the main challenge that we have seen is that there is still a lack of awareness about enhanced weathering, and that's not only with farmers, but it's also with scientists who are work with soils and plants, with policymakers at the ministries. In terms of the farmers, what we found was that the farmers that tend to adopt this kind of technology earlier, they tend to be more willing to experiment. They tend to be more willing to, say, reserve a part of their land to say, oh, this year I heard about this new product. Let me try it on this part of my land. That was the case with the lettuce farmer. They actually started using wollastonite in one part of their field. Then in the second year, they went to another. In the third year, they expanded even more. The potato farmer that we work with, they wanted to try out wollastonite. So they took one of their fields and split it into two. So wollastonite on one side and no wollastonite on the other. And all we had to do there was go there and sample their soil, because they had already done all the work of deciding how much to add, spreading the wollastonite. So that was a way of getting into the market and into the minds of these farmers. But we do see that we have stagnated to a certain point unless there is more public awareness. In the last couple of years, we have seen more public awareness, and we do see more farmers adopting this. We even see new mining companies coming up. Now there is a second wollastonite company here in Canada. They're mining in Quebec. And one of the reasons why they're mining wollastonite in Quebec is because they heard about the different uses of wollastonite beyond those traditional markets.
Yeah, so could you give like a summary of maybe some of the co-benefits of wollastonite for enhanced weathering compared to other minerals? I know you mentioned previous work in the Netherlands using olivine, and I think you've touched on this question a little bit already, but do you want to just give like a quick summary or overview of that?
Yeah, so in terms of co-benefits of wollastonite or any other silicate mineral, so it might be basalt, it might be serpentine, any other mineral that we wish to add to soils to sequester carbon. Ideally, we have co-benefits, which are improvements in plant growth, which are improvements in soil properties, so that farmers have additional reasons to use this. When we think about the agricultural economics, we find, for example, that fertilizer is one of the main costs in agriculture. So if they have a soil amendment that has even the slightest fertilizing ability, they might be able to actually save on the fertilizer to be able to spend on the mineral. So there are not only chemical and biological benefits, but even economic benefits, perhaps, to using these minerals. And that's not even counting the ability to claim carbon credits, which today there's no possibility to claim carbon credits yet. But there's still a lot of economic incentives to use minerals if there are some other benefits that can be achieved.
Awesome. And I'm wondering, right, like with all of this, like, understood and researched, what are some of the key open questions and obstacles left for us to understand as we try to further enhance weathering and take this and scale this globally? So
a couple of challenges, I would say. One is that some minerals contain trace metals. That's not the case of wollastonite. The wollastonite that we use is a certified agricultural soil amendment. It's even certified to be organic. So it's a very safe mineral to use. Some other minerals, such as basalt and serpentine, they may contain some metals, and there has been a lot of work on trying to understand what is the risk. Is there a risk that the nickel or other metals in these minerals could pose to plants, soil, and especially, of course, to humans who might consume the foods grown in those fields? And of course, it's a question which depends on a lot of factors. It depends on the mineral, it depends on the soil, it depends on the climate, it depends on many things. So we don't have a very reliable answer yet on what level of metal content in the mineral is safe. I believe there is currently a regulation regarding this in Brazil because they have regulated soil remineralizers, which are minerals that you add to soil to provide potassium and phosphorus and et cetera. But they are aware that those same minerals contain metals. So I believe that regulation has specified some limiting values, but we have to always remember that any regulation that has limiting values sometimes are not based on risk. They're based on other factors to come up with those limits. So we do need to do more work on that. The other area which we still have to do more work is how do we verify the carbon sequestration? And when would we be able to give carbon credits for someone using the minerals? So one possibility, for example, is that you issue carbon credits simply by the fact of applying mineral to soil. So today I've applied this many tons of mineral to soil, I should be able to get this many carbon credits. Well, that approach would be possible if there is confidence in what will happen to the mineral in soil. So that's why our field trials and modeling studies are trying to build that confidence so that the carbon credit can be given upfront. If it's not possible to give carbon credit upfront, then we would rely on actual verification. And as I discussed in my presentation, actual verification can be tricky because of the migration of carbonates down into the subsoil. At some point, a few years later, you won't find the carbonates anymore in the top portion of the soil. So how do you verify? So these are still some of the open questions, and maybe the reason why the current issuers of carbon credits don't yet consider enhanced weathering to be a 100% reliable technique because of the uncertainties that remain. But it's something that we should be able to overcome in the next few years.
Yeah, actually, to follow up on that line of thought, how do you think about permanence and durability for enhanced weathering? I know that for regen ag, like different agricultural practices are known to be kind of fickle in terms of their storage of soil carbon. How does enhanced weathering compare to that? And what are kind of some of the methods that you briefly mentioned, I think, around modeling that help give us more confidence of where the carbon is actually going?
Yeah, so what modeling does is it helps us to explain the mechanism. If we can understand the mechanism of enhanced weathering, then we can have confidence of how it will behave. And what modeling does suggest is that the migration of the alkaline earth metals into the subsoil is followed by the migration of carbonate and bicarbonate ions, right? If calcium and magnesium are going down into the subsoil, something has to be following them. It's a principle of geochemistry. We need to have electrical neutrality. If cations are going somewhere, anions have to follow them. And so the idea is that the anion that would follow them would be carbonates and bicarbonates. So modeling can give us that mechanistic confidence. And the other confidence that we can have in enhanced weathering is history. Enhanced weathering is something that is the basis of soil formation from a geological point of view. All soils in the world were formed by the enhanced weathering of sediments that accumulated on land and eventually interacted with rainwater, and soil became to be soil. So that confidence is something that we can rely on to essentially estimate that enhanced weathering should have a permanence of the order of probably decades, but even more likely centuries and perhaps even longer. One of the considerations that we can think of is how long does it take for an ion to migrate from the soil all the way to the ocean? And what studies show is that the residence time is in the order of decades to centuries. So that already gives us some confidence. And even when those ions do end up in the ocean, the other confidence that we have is that the ocean is a very large carbon sink already. And so adding a few extra gigatons is something that the ocean should be able to handle, especially again, if we are geochemically stabilizing it, right? It's one thing to pump CO2 into the ocean and hope that it stays there. Well, that's not very geochemically stable because we're only putting CO2. But if we're putting minerals and CO2 together, it's a much more stable system. It's based on principles of thermodynamics. You're going down into more stable states of chemistry, and so it should be relatively stable.
And just to follow up on that, you talked about the challenges of modeling and providing guarantees. Do you have any sense of like what the carbon markets are moving towards, and if different carbon markets like Verra or Gold Standard, or even these new direct purchasers like Stripe or Microsoft have expressed interest or trying to develop standards for this?
Yeah, so one idea I have on that is that one of the carbon markets that I tend to follow is the company called Nori, and they recently published a blog article where they discuss why they're focusing mainly on modeling and less on sampling. And one of the issues that they discuss, which is something that we have also observed, is that it's actually very difficult to do a full carbon balance of any particular soil. You go to a farm, the farm has 100 hectares. How do you determine how much carbon is there today and how much carbon will be there in 5 years and 10 years? Soils are heterogeneous. So that means the properties of soils change from place to place. So do you take 10 samples, 100 samples, 1,000 samples? Soils are also very heterogeneous in terms of depth. You go 15 centimeters, you have a certain layer of soil. You go 30, you go 60, you go 1 meter, 2 meters. So how do you actually account for all the carbon in the soil in a reliable way so that you can come back next year and do it just as reliably? It's very difficult. It's very complicated. It's expensive. So NORI has been focusing mostly on modeling to make the process feasible for farmers. And it's something that we also should be considering for enhanced weathering. One of the possibilities with enhanced weathering, for example, is to simply trust on the stoichiometry. If I have a certain mineral that has this much calcium and this much magnesium, and I add it to soil, well, if I can more or less confidently expect that those calcium and magnesium ions will result in the formation of calcium and magnesium carbonates and bicarbonates, then I can trust the stoichiometry to issue the carbon credit. That's not always going to work because some rocks or many rocks are made up of more than one mineral. For example, the wollastonite that we use is a combination of wollastonite and diopside. And what we see in all of our experiments is that the wollastonite weathers, but the diopside remains. Is it because the diopside will not weather? Oh, it will probably weather, but it will weather more slowly. So instead of taking months or years, it might take decades or centuries. So we even have to be careful if we use something as simple as stoichiometry. But it's something that we need to consider. What is the best way to estimate so that we can have relative confidence and we can avoid very expensive sampling and verification?
Yeah. I'm wondering, Professor Santos, it seems like to get some of this verification and development done, it'll have to be research and farmers and industry and a lot of different people working together. And it seems like when you came up with this idea for wollastonite and enhanced weathering, you were also looking at farmers and talking to farmers and how they were using it. How do you think research will work with industry and different stakeholders when it comes to some of these technologies, right? Like, what's the role, or how do we work on enhancing that connection between research and industry?
Well, what I find, for example, is that in agriculture and farming, there are certain trusted sources of information that farmers have. Farmers rely very heavily on what, say, the Ministry of Agriculture suggests. They have several manuals about if you're trying to grow corn, do this. If you're growing soybean, do that. There are also many consultants that farmers use to give them advice about what should I be planting this year, what fertilizer should I be using, how much should I be using. And these consultants, what they do is they go to the farm. Sometimes they collect samples. They send it to a lab. They get an analysis result, and based on that, they give advice. What we have been finding again is that the awareness about enhanced weathering seems to not yet have reached some of these stakeholders. So it seems that the government is not quite yet aware of it. Consultants also are not quite yet aware of it. And so it has to start somewhere. It's a cascading effect. If today the Ministry of Agriculture here in Ontario, which just happens to be right beside our university, if they issue the funding call or a guideline for enhanced weathering is something that's coming up, we need to learn more about it, or we're looking for farmers to do demonstration trials, that would create a cascading effect. Farmers would hear about it, consultants would become aware, suppliers of minerals will become aware. So we do feel that we are missing this ignition. Once we have the right kind of ignition, everything can unfold much more quickly.
That's interesting. What do you think is going to be that ignition, or I guess how do you think we can activate more stakeholders in this enhanced weathering field?
It's difficult to say. I mean, if I had the answer, I think it would have already been happening. But it's something that we don't want to overly rely, let's say, on government regulation to drive something. Although sometimes that's just the way it is. With many pollution mitigation measures, it was government regulation that eventually got things going. But there might be possibilities for the private sector to to drive this in a faster way, perhaps is the availability of the carbon credit that's still lacking. Maybe we just need a new company to come up and say, well, look, we're going to take the risk of this enhanced weathering. We're going to start issuing carbon credits. We'll come up with a way to verify and get things started. Right. So someone needs to get started. Until today, the main thing that we see is that farmers are only using these minerals if they see a benefit to their bottom line. So either their plants are growing better, or they're saving on fertilizer, or they think that they can grow more crop cycles because of better soil health. So and that's working, but that only works again to a certain extent. Not every farmer is looking to change the way that they do things. So we do need some additional incentives to get this scaled up even faster.
Yeah, I was just going to say it's convenient that, Wollastonite is already being used by farmers strictly because it helps their crops. So not even for the carbon benefit or anything else. So that's always nice. You have some sort of revenue already coming in, or some sort of benefit outside of just the carbon sequestration, which is always really good to see in different technologies because it helps them scale and gain adoption quicker. I wanted to ask, since kind of just to continue more on how we can continue to push enhanced weathering, OpenAir is a community full of people passionate about carbon sequestrations, and we have a whole lot of different folks there, scientists, engineers, and others involved in activism and business. Are there any problems or things that you're working on right now that our community could help you with in some way?
Well, I would say that the main thing that we're still lacking is the ability to form field trials that are at the scale and quality that government institutions are looking for. Essentially, a government regulation will not be set up based on plot trials or microplot trials or a few scattered field trials. They need very consistent, massive trials. And that's something that we still lack. So we do need someone to take that chance, do a very large scale trial with all the data that's possible to collect, and hopefully use that as the demonstration for this technology to be implemented. We do have a couple of ideas of how we can try to achieve this here in Canada. So we'll see if we can make it happen in the next few years. But if we can get additional help on this, you will definitely be welcome.
Great. We'll definitely drop a line in our Discord. And if anyone out there is interested in helping out with that, do feel free to reach out to us. So with that, we just want to thank you for taking the time to chat with us and sharing about your research, Professor Santos. It's definitely been really exciting to hear about the field work you're doing. And we definitely look forward to continue to helping you support your work.
Yeah, thanks a lot for having me.